Hello, I am Mélissa Rossi. Together with James Howe, we will present a joint work that was done with Thomas Prest and Thomas Ricosset. We studied several aspects of isochronous Gaussian sampling. Let us start with the motivation of this work, namely Falcon. It is a lattice-based round-3 candidate for the NIST post-quantum standardization process. Falcon is based on the GPV framework, and it is the only hash and sign candidate for the standardization process. It relies on n-true lattices and fast Fourier orthogonalization. It provides the most compact signatures in a sense that the sum of the sizes of the public key and signature is minimized. Let me briefly sketch the underlying idea. To generate a key pair, we generate two matrices A and B with coefficients in a polynomial ring such that B times A equals 0 and B has small coefficients. So the public key is A and the secret key or private key is B. To sign a message, we compute C such that C times A equals h of m. Since we do not require C to be small, this step can be done easily. Then we find a vector v in the lattice generated by B that is close to C. We can do that because C is supposed to have small coefficients. Then the signature is simply C minus V. To verify a signature, we verify that S is short and that S times A equals h of m. Indeed, if we replace S by C minus V, we see that V times A equals 0. It is because V is in the lattice generated by B and B times A equals 0. This work has been initiated during the round 1, and Falcon presented from the start several advantages, like the compactness and the fact that it is very fast. It also relies on strong proofs in the random oracle model and in the quantum random oracle model. This might be why it has been selected in the round 2 and recently in the round 3 as part of the 3 selected signature schemes. However, on the downside, Falcon was not the best implementation-friendly option. It is non-trivial to understand and implement, it relies on floating point arithmetics, and the side channel resistance was not very well studied. It was even the target of several side channel cryptanalyses, like the timing attack that was published in Eurocrypt this year. More generally, the Gaussians in Falcon are the problem. They are the target of the attacks, and they induce several implementation issues. Thus, Falcon needs a simple way to generate timing-protected Gaussians. When we think of timing protection, we often think about constant time as a countermeasure. However, constant time might be a confusing term. Indeed, constant time does not really mean that the execution time should be constant. We actually require the execution time to be independent from the private key, which does not mean that the time is constant. To avoid any misunderstanding, in this work we prefer to say isochronous. We will also assume that the elementary operations are constant time on the integers. This work can be decomposed into two parts. The first part is the introduction of a new Gaussian sampler for Falcon. This sampler is simple, fast, and uses only integer arithmetics. We also provide security and isochrony proof. In a second part, James will present a new statistical test suite that we called Statistically Acceptable Gaussians. He will also present our implementations. In Falcon, the tricky part is the second point of the signature. It relies on an algorithm that's called FF sampling, that itself calls the Gaussian sampling over the integers. If we want to protect Falcon against timing attack, the important thing is to protect the Gaussian sampling. Indeed, all other operations do not use conditional branching. Various Gaussian samplers already exist in the literature, but here we present a simple alternative dedicated to Falcon. The underlying idea is very simple. We construct a distribution that looks somewhat like a Gaussian but is not statistically close, and then we use rejection sampling to correct the discrepancy. One important detail is the fact that the parameters may vary. The standard deviation is between a sigma mean and a sigma 0, and the center may be between 0 and 1. So at one point we should draw an element from this Gaussian, or even this Gaussian. To overcome this issue, we introduce a three-step technique. The first step is to draw an element z0 from a centered half Gaussian of standard deviation sigma 0. The second step is to flip a coin, so draw B uniformly at random in 0, 1. If B equals 0, then we take minus our sample, and if B equals 1, we take our sample plus 1. We end up with a stretched distribution, which is flat at the top. In the third step, we use a rejection sampling technique to recover the target distribution. More specifically, we will accept our sample with a probability that is the ratio between the blue distribution and the pink distribution. Here is the overview of our Gaussian sampler. And we can recognize our three steps. In the last step, if we compute the ratio, we see that it is the ratio between two exponential. For isochrony purposes, we had to make several changes. In the implementation, to draw the first sample z0, we use a cumulative distribution table. We also use a polynomial approximation for the exponential and make the number of iterations independent from the secret. We also used Rényi divergence results to prove the security and isochrony. First, we prove that our sampler is isochronous with respect to the standard deviation, the center, and the sampled value z. Besides, we prove that using our sampler on the lambda bit secure signature scheme provides lambda minus 2 bits of security. We particularly rely on a Rényi divergence result that was provided by the literature. Let me present a technical issue that we had in the proofs. In this theorem, in the first hypothesis, we see that we assume that the infinite norm is bounded. However, it suffices to assume that the Rényi divergence between these two distributions is bounded by square root of 2. To apply this theorem, we need the distributions P and Q to be two distributions of an tuple of variables. Later, we use a multiplicativity result to recover the Rényi divergence of P and Q. If we have a specific bound on the marginal distributions Qi and Pi, we can recover our hypothesis. However, the multiplicativity result can only be applied if the distributions Pi are independent. So this works for the Fiat-Shamir-Witherboard signatures, but it does not work for Falcon signature, where the standard deviation and the center are dependent. To overcome this problem, we introduce a new multiplicativity result that does not require the independence. Our requirement is stronger though. We assume that the Rényi divergence between the marginal distributions, assuming any initial conditions, is bounded. We end up with the same bound on Q and P. Let me present the three modifications in more details. For the base sampler, we use a cumulative distribution table, CDT. A CDT sampling can be done isochronously if the algorithm reads the entire table each time and carries out each comparison. With a simple script, we can generate such a table. For Falcon, only 19 elements of 72 bits are necessary. We then use a polynomial approximation for the exponential. We need a polynomial that validates several inequations, as written here, and several tools are possible. We can use FACT that had been provided in 2018. But for an integer option, we prefer to use galactics that was provided in 2019. We recover a degree 10 polynomial with 32 bits coefficients. However, depending on the architecture, several trade-offs can be made. We can minimize the degree, or the size of the coefficients, or the depth of the circuits. Finally, we had to make the number of iterations independent from the secret. Originally, the number of iterations could possibly leak the secret. Indeed, the number of iterations follow a geometric distribution of an average that depends on sigma and mu. So we actually tweaked the acceptance probability by scaling it by a factor. This factor is sigma mean over sigma, which is no larger than 0.73. This means that we will reject more signatures, but with this tweak, the average number of iterations becomes independent from the secret. We can see it using a Poisson summation equation and simplifying the ratio. Thus, our timing is now independent from mu, sigma, and the sample z, which means that our whole algorithm is isochronous. I now let James present the second part of this presentation.
So as Mélissa said in the introduction, our second contribution is a statistical test suite for the univariate and multivariate distributions found across many schemes within lattice-based cryptography. We call this SAGA, that is statistically acceptable Gaussians. And this is really motivated by the fact that mistakes are clearly possible, and these can also be of many different forms. So implementation failures, which was even seen in a mistake during an implementation of Falcon recently in their table values for the Gaussian distribution. And things like this are pretty easy to do, as the outputs can look fairly Gaussian, and it isn't until you analyze them that you can see something's wrong. And other types of mistakes you might find are like misunderstanding the theory or underestimating your entropy requirements. And the good thing about SAGA is it just works on the data that's output from the sampler or the scheme, and it's thus like agnostic to whatever method you use to derive this data. SAGA can therefore validate univariate samplers, univariate Gaussian samplers, such as those seen in Bliss and Frodo, multivariate Gaussian distributions, which you will see in outputs of Falcon or anything Falcon-like, such as IBE schemes or GPV-based signatures. And as much as possible, we also try to back up the statistical tests with visuals for further sanity checking, where we can check for things like rejection rates as well, for example. So for the base univariate Gaussian samplers, we provide a simple set of tests which look at the data's first 4 moments, checking the empirical mean, variance, skewness, and kurtosis. And then we compute the chi-square test to further ensure normality. And visually, we can also see this by plotting the expected and empirical distributions, as well as looking at stuff like QQ plots and R-squared values. The multivariate side of SAGA is much more interesting. We first developed an ad hoc test for the covariance matrix of the multivariate samples, as this should be close to the identity matrix. So we posit that summing the block subdiagonals of this should grow in big O of the square root of n for correct implementations and big O of n otherwise. And using this, we can then compute another chi-square test to validate the multivariate data. There also exists multivariate normality tests. We surveyed these in the literature and found the Dornick-Hansen to be the best for our use case. Essentially, the others lacked the statistical power required for the high dimensions found in lattices. So we then come to the supplementary tests, which are also pretty ad hoc and essentially aim to visualize the normality. And obviously visualizing beyond 3 dimensions is very difficult. Thus we use the Mahalanobis distance, which tells us how many standard deviations each point is from the mean. And then we can use this in a QQ plot as the distances from a normal distribution. That's the Mahalanobis distances from a normal distribution should follow a chi-square distribution. We also know that the rejections or repetitions in samplers should decrease geometrically, and we can add a simple repetition counter into these and then model this to visualize a geometric decrease, as you can see here. That's pretty much everything from SAGA, and finally we come to the performances of our proposed isochronous sampler. So we provide results on a single core of an Intel i7 CPU. The results shown here are when we integrate the sampler into Falcon. We also provide provide results of the sampler on its own in the paper. But with respect to Falcon, we see a minimal performance degradation for complete isynchrony. So between about 13 and 18%, depending on whether optimizations or which parameter set is being used. And this really shows that this method is a great candidate for trapdoor sampling. And we see this as a great step in making Gaussian samplers more robust and more trustable for real-world implementations. Thank you for listening.